Okay, so let me first thank the organizers to invite me to this nice place. And what I will try to show you, Shushun just showed you that the kicked rotor is very interesting for theoreticians. And now I will try to show you that it's also interesting for experimentalists. This work that has been done for many years in a collaboration of 3 labs, the FLAM in Lille in France, LPT in Toulouse, and LKB in Paris, at l'École Normale Supérieure. So if you put them on a card, you see that Lille is in far north of France, and LKB in Paris and Toulouse in the south, so we do a diagonal over France. So this is the people involved in this group. So some of them are mixing here, so I took another photo to show you, and this shows us that we don't meet only to eat, but also to do some experiments. So the talk is globally about quantum disorder, and I show you that this mapping that Shushun explained before, connecting the kicked rotor to Anderson model, can be exploited in experiments to measure real experimental quantities. As Shushun explained you very well these things, I won't come back to that. I will just assume that you remember these points, that dynamical localization, which happens in the kicked rotor, is localization in momentum space, not in the real space. It corresponds to an asymptotic in time saturation of the kinetic energy of the system. So as any Anderson model, the system is always localized in one dimension, whatever the disorder. This is a standard property of Anderson model. And then if you go to dimensions higher than 3, in this case you have a transition from localized in strong disorder and diffusive system in a small disorder in diffusive systems. And I will assume also that you know the essential things about cold and ultra-cold atoms, very, very simple things. Okay? So my aim is to show you that the atomic rotor is an almost ideal quantum simulator for Anderson models. And I just remember you in a transparency, what's the kicked rotor? It's just a particle turning on an orbit with free motion, and then periodically you apply a force to it, what we call a kick. And if you write the Hamiltonian of that, you shouldn't have just done it. You have a kinetic energy term. And then here is the periodic time, kicks in time. The kicks are instantaneous, okay? So it's very, very simple. It's very easy to simulate numerically because this is free evolution. This is just an instantaneous force. This is one of the large forces interests of the kicked rotor. If you do it classically, if you do it quantically, it's also very simple because this is diagonal in momentum space, this is diagonal in space, in user space, and the two are connected by Fourier transform. So it's very easy also to simulate it numerically. Now, what we like to do is to implement that with cold atoms. And this can also be done in a quite simple way, just by putting an atom to interact with a standing wave, for example. The essential process is this one. You have the standing wave that is formed, by 2 counterpropagating beams, and then the atom will absorb a photon in one of the beams and emit it on the other beam, making a transition with no spontaneous emission. All elements of this transition are stimulated. So there is no dissipation in the system, which is obviously very important to keep the quantum character of the system. So what happens is that you take a photon here, put it here, so the atom must recoil to conserve momentum. So momentum after should be momentum before plus 2 times the momentum of the photon. If you want to write this as an average force, this average force will be just this momentum exchange times the photon exchange ratio that you can easily calculate for a 2-level atom, for example. And this gives you a force that has this form. It's a gradient of a function. It's thus a conservative force, okay? It turns out that the potential, this force is associated to a potential which is called the optical potential, which is proportional to the intensity of the laser beams, inversely proportional to the detuning. And if you take a standing wave in which the intensity is modulated in space like that, you just give this kind of terms. So if you do something very simple, you put an atom, you let it in free motion, and then at some times you come with your standing wave to apply a kick to it. The standing wave is put on and off very quickly in order to create this potential. And if you write the corresponding Hamiltonian, it is exactly the same as the Hamiltonian of the kicked rotor. The difference that now here, this is just linear momentum, and this is just space, but it's essentially the same thing. So when you write normalized, these Hamiltonians written in normalized units, so you can calculate the commutator of these two quantities, and you find it gives effective Planck constant introduced by Schuschun. He called it HA. I use the notation of Raisen, K bar, it's experimentalist notation. And in this particular case, you can calculate it explicitly in terms of atom and the light field properties, okay? This has been done for the first time by the group of Mark Raisen in 1995. Now, what's the classical motion of the kicked rotor? What happens is that your atom, you apply a kick to the atom, and the atom will move, and then you can apply another kick, and it moves again, and then you do another kick, and it moves with a different velocity, and so on. That's a quite simple motion. You can continue like that for many kicks. The important point is that the force of the kicks that is characterized by this parameter K, the stochasticity parameter, is greater than 5 in these reduced units. Then you can plot a phase portrait of the system. You have X and P, and you see that it's almost ergodic. This means that if you show some initial condition here, your trajectory will be a complicate trajectory. I don't know, like this is just an arbitrary one. But you see that in P, it will be like diffusion in energy, okay? So this was the principle. Now, this is the real experiment with cold atoms, though, so it's much more complicated, but it's still a simple experiment compared to many others. So these are some views of the experimental system. And what you got with that is that if you just apply kicks and measure the momentum distribution, we can see, well, here it's difficult to see directly, but we started with, this is experimental, we started with a Gaussian here, the thermal distribution here in momentum, and then you let it evolve. You have some fast evolution here, which is the classical diffusion, and then dynamical localization sets in. You see that it's not anymore evolving, and at the end, if you look here, you'll find that the shape is an exponential, exactly as predicted by for an Anderson model. Okay, so Schuschun told you that if you put new frequencies here, donc my previous Hamiltonian just don't have this term, epsilon equals 0. I changed it just by modulating the intensity of the kicks with 2 incommensurate frequencies, and Schuschun explained to you that this maps to a 3D Anderson model. The real system is always 1D, but it maps to a 3D Anderson model. The interesting thing is that in 3D you have an Anderson transition. So what we try to do with our experiment is to see this transition. So this is the same figure Shushun showed you. This is the parameter space of this system with two parameters, k, the amplitude of the kicks, and epsilon, the amplitude of the temporal modulation here, okay? And you have here the black line is the point where the transition occurs. Here you have diffusive states, metal, and here you have insulator state, that is dynamical localization. And you can cross this transition experimentally, for example, by going from here to the transition and then to the metal region, okay? And you expect, effectively, what we observed experimentally is that here you have some localized exponential wave function with a momentum, average energy that is constant asymptotically. Here you have diffusive behavior. The wave function, the momentum distribution is a Gaussian. And then here is the critical point. It's somewhat special, but it's possible to calculate it analytically, and it turns out to be an Airy function here. So this has been done in 2008 in our group. And then, as this is the publication, as Shushun explained to you, we have been able to do a finite time scaling of this system because the number of kicks is not very large, so we have to extrapolate it in some way to an infinite number of kicks, exactly as when you do it in solid state physics. We have to extrapolate it to an infinite crystal, and the measurements give this critical exponent experimentally. Numerically, this has been done in the group of Paris by Gabriel Lemarié, and this is quite good agreement. And this is the most recent precise measurement by numerical simulation directly on the Anderson mod by Slevin and Otsuki. Okay, so it's a quite good agreement with that. This at least shows that the kicked rotor and the Anderson model are in the same universality class. So let's talk a little bit about universality. This is the next paper we have done. The idea of universality is that the critical exponent cannot depend on experimental parameters. So if you change the mass of the atom or some of the parameters of the problem, and or the way you cross the transition, the critical exponent must be the same. So what we have done is to take these sets of data with different parameters and measure the critical exponent for all of them, and you see that they are in good agreement with the theoretical prediction. So we have also looked for the phase diagram of this transition experimentally, and the result is here. This is the same diagram as before. Here is the metal part, here is the insulator part. This is numerical. This is the transition region, okay? The opening here is the numerical error, so the transition is just here, okay? These are the theoretical models that you can compare to them. They do not reproduce very well these numerical results, but the experimental points are in perfect agreement with the numerical simulations. We unfortunately cannot go on this side experimentally because of experimental limitations. It would be interesting to see if the experiment can see these oscillations, okay? So this is not anymore unpublished. We can also look for the Anderson localization in 2D, which is interesting because it's a pathological case. I told you that in 1D it's always localized, whatever the disorder. In 3D you have a transition. In 2D it is an intermediate case in which it's always localized, but if you lower the disorder, the localization length goes to infinity. So we can also see that this is just numerical distributions for different number of kicks. These are 2D models, so we have only one frequency here, not anymore two, because otherwise it will be 3D. And this is typical what we see. at 0 kick it's well localized, and then it becomes larger and larger. This is exactly what's expected. We can check that the form changes from an exponential if I take a log scale exponential is a triangle, and in the wings it's a exponential, and then for larger number of kicks it will become a Gaussian. But here it's not a Gaussian, so it's perfectly localized. And then I can change this parameter. You see that if I put epsilon equals 0, I have 1D. If I increase epsilon, I go progressively to 3D, and I see that the distributions become larger and larger. And we can even check that as predicted for the Anderson model, this behaves as an exponential. It's an exponential function of the disorder that is characterized by these parameters. So this is, to my knowledge, the first time one has seen this behavior for the 2D Anderson model. Now I shift to another effect. Shushun has talked also a little bit about that, which is weak localization. What is weak localization? What happens here? You see, this is p square, this is the kinetic energy. So classically, you expect it to diffuse linearly with time, and then dynamical localization is the fact that this will saturate at long times, and weak localization is what happens in the beginning, when we are not anymore completely classical, but we are not completely quantum anymore. This time regime is very interesting, happens very interesting things, and can be modelized analytically. So one of the findings of this is that it strongly depends on the system symmetries. So it's a very good region to test universality, to see in which universality class the system is. For example, if the system is time reversal invariant, it is on the orthogonal class. The orthogonal class is defined as the spinless system invariant under time reversal. Unitary class is when you break time reversal invariant, but you don't put spin. And if you put spin and you keep time reversal, we are in the symplectic class. This is difficult for us because for the moment we have not done any kicked rotor with spin, but we can check these classes here. Okay, so how to do it? With this Hamiltonian, I can easily show that it is on the orthogonal class, because you know that time reversal invariance is to put p to minus p, t to minus t, and if you do this doesn't change. It's in here you have just to use the properties of the delta function and change the definition of this index to show that it's invariant. So this simple Hamiltonian is on the orthogonal universality class. Age transformed is equal age. Now, this you can relate this. You can show that this is the same thing as to say that the quick series, this is time, and this is the kicks I am applying periodically. This kick series is symmetric in time. If I revert the sense of time, you see that the sequence is exactly the same. That's no difference. Okay. So what I try to do, this is obvious orthogonal, is to find sequences that are not so. How to do that? I should break time reversal invariance, and this can be done with period 3 sequences. This is an example of a period 3 sequence of kicks. You see that the sequence is periodic. This is repeating itself, but inside each period you have different kicks. Okay, and in this case you see that the kicks are increasing and then increasing, so that if I revert this series, I put the time on the other sense, you see that it's not the same thing. Here the red and the black kicks are inverted. So this is a sequence of kicks that not time reversal invariant, and this time reversal invariance is just broken. Okay. What is interesting in this case is that I can just simulate this by putting some well-chosen modulation here. Here I'm using rational periods here. So this is just period 3, and you see that with this period 3, I just reproduce this kind of a symmetric sequence. And this allows us to break the symmetry in a controlled way. I show this is just the sequence I showed just before, but if I just add some, change the phase of this sequence, I just displaced this sinus function a little bit from here to here, and this sequence you can see that it is symmetric around the red peaks. Okay, so I transformed an asymmetric sequence in symmetrical sequence just by changing a parameter. This means that we can control the symmetry breaking by just changing one parameter in our Hamiltonian. So how to detect it experimentally? Here's one way to do so. I won't go into any details, but just tell you that if the system is time reversal invariant, here is the momentum distribution, which is supposed to be a Gaussian, but this is a numerical simulation. Here at zero momentum, you have an enhancement of a factor of 2 of this system. This is because the trajectories that go in one sense in time and the other that go in this opposite sense in time will interface constructively because the system is invariant on this changing. So the presence of this peak here allows you to see that you are in the orthogonal class. Okay? This is just a numerical simulation of the same thing. Why I do that? Because it is sensitive to the width of the initial state. So in order to do that, either I have a very low temperature of my cold atoms. If I don't have that, if I increase the temperature, the contrast of this peak diminishes and it becomes difficult to see. But there is a simple way to do that, is to make a period 2 Hamiltonian that is invariant over this time reversal, and then you change from a period 1 to a period 2. This means this enhanced return to the origin, this enhanced peak, will appear only one kick over 2. In even kicks, you have this peak, and in odd kicks, you have not this peak. And this even the signal is not very strong here. By contrast, we can see it very easily. Okay. Now, and you see that I can I'm just plotting a function of time this signal here, and you see that here's for even kicks it's larger than for odd kicks, and the reason the contrast is diminishing is just the coherence in the system. That's a break in the phase coherence and thus destroying quantum interference. Well, how much time?
About 10 minutes.
Okay. Let me just show you how we can engineer more complicated sequences by combining this kind of Hamiltonians. I put here a Hamiltonian in which I modulate the intensity of the kicks and I shift the phase of the standing wave. This is not very interesting for theory, but for experimentalists, it gives you new parameters in which you can, with which you can play. That is very useful to do this. Here I put a 5 here, period 5 here, and 2 values of this shift of the standing wave, and I get a period 10 Hamiltonian. In this case, because I'm playing on time and space, the relevant symmetry is not T, it's PT, the product of parity by time reversal invariance. It's just a detail. So I take this complicated Hamiltonian and I will play with it. So I choose phi equals 0 here, and I can construct a symmetric. You see that this sequence of kicks is symmetric. Okay, it has, for example, a symmetry axis here. This is symmetric of that, this is symmetric of that, and so on. This is thus an orthogonal sequence. But if I choose another value of the phase, then I construct some asymmetric sequence which I can say just by inverting it. You see that they are not the same. This is unitary. So an interesting point here is to know where, in which kick you see the signal, the enhanced return to the origin signal. It's very simple because the system is symmetrical about this point. So if you prepare this initial state here, you just see the signal here at the symmetric with respect to this axis of symmetry. Okay, there's other small problems here, but I won't go on there. Let me just come back to this. So I realize a sequence like that. So I start here, the axis here, and I expect my signal to be at kick 6. Okay, and this is what I see when I do an experiment with really cold atoms in this condition. Yeah. You see that this is the average signal, and this is the signal at kick 6 that shows these peaks, and this is the signature of the orthogonal class. And if I do an experiment, I find something like this. I see these peaks at each 6 modulo 10, because I have a signal here, but we will have another signal here after an entire period of the signal. What is interesting here is that is another peak here. And for the moment, I don't know what is this peak. I will try to show it later to you. Okay? So this is just a zoom of the previous thing. And so now, what I do is that I construct, by changing the phases, this unitary sequence, and the peaks at kick 6 modulo 10 disappeared. The other peaks that remain here are these peaks that I don't understand, I have seen before. But they are not at modulo 6, but at modulo 0. Okay? So you see, you can compare the two sequences. You see that here you have two series of peaks, and here just one. So I have effectively broke PT symmetry in this system. Okay? Alors, what is these mysterious peaks that survive even in the unitary case? First thing, I see that they are smaller in the beginning, and then they increase progressively, and they arrive at this value, this constant value by the localization time. And this is, I won't go in this explanation in detail. One can show, this has been put in evidence recently, that they are related to more complicate loops. I told you that if I have something like that, okay, let me just go fast on that. Okay, suppose I have this a system that goes in my media, and it is scattered in this way. It enters here, and then it does that and that and that, and go out here. Okay, it will have a phase phi top from this loop and phi bottom from this loop, and then I can imagine that I will do it in the other sense. That is, I do the same loops, but in different order, I get the same phase. So these loops will interfere. These two signals, green and blue, will interfere. But if I do time reversal invariance here, I change the signs of the phases, but I change the phase for both, and the complete phases are still equal. So this is a sign that called coherent forward scattering that survives to time reversal invariance breaking. And this has been put into evidence relatively recently by numerical calculations. I won't go in details. And to my knowledge, our signal is the first experimental observation of this phenomenon. Okay? Another way, and just conclude there, to put in evidence this changing in universality class, it looks for the transport property of the system. This is characterized for people that know that by the Anderson's beta function, that just a measurement of the behavior of the system, the conductivity of the system. And the expected behavior is very different For orthogonal, it's linear here, or it's parabolic for unitary. So if we do an experiment, we have done an experiment, and you find that it agrees with this characterization by the beta function. Okay, so let me conclude. I hope I showed you that ultra-cold atoms are a powerful tool to the study of fundamental properties of quantum systems, and they keep wrote an excellent system to study interference, decoherence, and symmetries. What you can do with that now, we can look for, Shushun showed you that for early time dynamics of a kicked rod, you should see effects of the Herrenfest time. So this is something we have been discussing, and we have done some first experiments in Lille that effectively show that this happens. We can try to introduce spin in our system and go to the symplectic class where there is another interesting things. There is a quite old theoretical simulation of that, so we have a base on which study it. We can try to break the symmetries using other methods, for example, as suggested in this paper, in connection to quantum chaotic systems. And we can try, this interesting thing with our system, as I told you, is that with two supplementary frequencies, we have a 3D Anderson model. If I put one more frequency, I have a 4D Anderson model. So I can make measurements, experimental measurements, in a system that is effectively 4-dimensional or 5-dimensional. It's not so easy that it appears to be, but it can be done while working that. In particular, we know that the critical exponents depend on the dimension, and it would be interesting to see the difference between, for example, orthogonal, that is 1.57, unitary 1.43, symplectic 1.35, and then go to higher dimensions and see it. So I will stop here. Thank you very much for your attention.